Previously, we were taking a look at Newton's third law of motion. Now I'd like to transition into dynamics in two dimensions. This video is going to cover a couple of topics that don't mesh in well with the rest of the presentation, but some of it is necessary for what's heading along. The first of the two things I want to take a look at is ballistics with air resistance. So far, we've been generally saying neglect air resistance, neglect air resistance. And I've mentioned in the past that the reason we're doing that is because it's just plain hard to do calculations that take air resistance into account. This is because, remember, the magnitude of the drag for most situations is going to be proportional to the square of the speed, and importantly, the direction is opposite the velocity at all points. So that means that at any given point on the trajectory, like say this one here, the force of drag would point opposite the motion. And so this complicates things. It's not impossible in a lot of circumstances to solve this analytically, but it's definitely beyond the scope of this treatment. And most of the time, it's more convenient to solve this numerically. So what you see here is me having done just that, solve it numerically. What you have here is what you would have if there was no air resistance. And you can see here that the trajectory is a parabola. Here, the green curve for the same launch speed, this is with air resistance. Now, I did choose an object that would experience a lot of drag, a pretty high coefficient drag, just to make the difference more pronounced. But this sort of thing is a typical behavior. You'll notice the trajectory is not a parabola. It's not any particular simple curve, in fact. And you can see you kind of go up and then you dunk down. And that's common, sort of a common trajectory for things with air resistance. What this means is if you're trying to go for distance, you're actually going to want a shallower launch angle. And the reason you do that is to minimize the hang time so that air resistance, so that and that you maximize your horizontal component velocity, so that a fast horizontal component velocity combined with a shorter hang time will give you a longer distance than what you would get with what you would expect if there weren't air resistance. So I bring this up mostly just to show that it is more complicated and that air resistance is not negligible by any stretch. It's just that this is difficult to solve with the math that I'm expecting here. Later, if you take differential equations and or you study numerical methods in a computer class, then you can certainly go ahead and analyze this. It's not painful to set up, especially numerically. But you can see that the difference can be quite stark. So when we neglect air resistance, it's not because air resistance is in the real world negligible. It's just that it's very, very hard to solve right now in introductory level treatment. So that was one thing that I wanted to bring out. The other thing, and this as we turn our eyes towards revisiting circular motion, is the RTZ coordinate system. This is one that has some use in the world of engineering. Physicists often use a related system called cylindrical coordinates, but there is a bit of a technical difference between the two, and I'll mention it briefly just so that you're aware if you ever look at a different text later. So let's say you've got something going around in a circle in a plane here. Now the idea here is that at any given point we can go ahead and erect a coordinate system. And the r-axis will be pointed in towards the center of the circle. T will be pointed tangential, and then z is perpendicular to them both. And anywhere you go along here, r will be pointed in, t would be tangential, oriented counterclockwise, and z would be perpendicular to them both. Now, physicists use a slightly different version of this, where the axis would be pointed outward, and that's done to the r-axis would be pointed outward, and we would name the t-axis something different. That's what's called cylindrical coordinates, not what we're going with here. The reason it's done is to make the coordinate system right-handed, which has some application. This is what's called a left-handed coordinate system, so mathematically it's a little harder to play with. But for what we're doing in future videos, it's all just fine. So for instance here, if we're looking down from above, so here's my plane of motion, and I've got something going around in a circle like this. Let's say at this point here I've got, I don't know, a force. Let's just go with a force here. If this is my center of curvature here, we can go ahead and define this angle phi. And now the tangential piece would be what I get dropping here. This would be F tangential, and this would be F radial, which we've kind of seen this before when we were talking about circular motion. We're just trying to extend the idea. So the radial piece of my force would be F cosine phi in this case, and the tangential piece would be F sine phi. So this is a specialized coordinate system specifically for looking at things that are going around in circles. And in the next video, we will pick it up from there and start taking a look at uniform circular motion. So we'll see you over there.